Welcome to CEE seminar for water and environmental engineering, water resource and environmental engineering at UCLA. It's my pleasure to introduce Professor Sujit Datta, who is an assistant professor at Princeton in chemical and biological engineering department. He has got his BA in mathematics and physics from University of Pennsylvania, and also got a master's in physics in same university. Then he moved on to Harvard to get a PhD in physics, and then he came to California to Caltech to get his postdoc before he went back to East Coast. His research mostly on direct visualization of particles and hydrogel. And one of the things that really striking for me is that most of the scientific development in any engineering black box system is possible because you can see it. So seeing is believing. That's how I see his research, and it's pretty amazing. So that's why I really looking forward to this presentations. So it's all yours now.
Well, thank you. Thank you, Sanjay, for that wonderful introduction. And thank you all for being here. It's really a pleasure for me to get to share some of the research that my lab has done over the past few years. As Sanjay mentioned, I have been at Princeton for almost 4 years now, but I still fondly think about, remember life in Los Angeles, which is where I was a postdoc. So today I'll tell you a bit about some of the work we've been doing, studying the dynamics of various kinds of soft materials in complex 3D porous media. And I'll give 2 or 3, if we have time, examples of the kind of work we've done in this area. And but first I wanted to give you a broad overview of the work we do in my lab as a whole. So our focus is in studying the dynamics of soft and living matter in complex spaces. And so, we study everything ranging from fluids and immiscible fluid mixtures to polymer solutions and gels, colloidal dispersions, and cells and cellular communities, microbial communities. And as a field, we've learned a tremendous amount about these different classes of materials and living systems by studying them typically in bulk, homogeneous, uniform environments. But often we encounter these different classes of materials and living systems in complex environments, environments with strong structural heterogeneities and disorder and confinement, chemical gradients, flow. These are all factors that can greatly alter the behavior of soft and living matter. And that's what we focus on in my lab. And so what do I mean by complex space? What are some examples? Well, you're all very familiar with an example when you just walk outside of a complex porous medium. The ground beneath your feet is a wonderful example of a disordered porous medium, soil, sediments, porous groundwater aquifers, oil and gas reservoirs. These are all examples of porous media where you have solid grains that are packed together and housing a disordered pore space. So this is an X-ray CT image of soil taken from another group, where you can see these brown particles are the solid mineral grains that are packed together, and they house a tortuous pore space in between, through which fluids and chemicals and solutes and even cells have to move for a range of different applications. And so by studying those kinds of dynamics in situ, our goal is to develop fundamental insights to help improve water remediation approaches and filtration, develop cleaner oil and gas recovery approaches, and develop ways to sequester carbon dioxide underground. So these are some of the problems that motivate the work that we do. And I'll give you some examples of that today. I just wanted to mention also, another example of a complex and heterogeneous environment that you are all also very familiar with is the gels and tissues in your own bodies, which are, porous, disordered macromolecular networks whose structure underlies their biological function. I won't talk about that today, but that's also a class of problems that we're very motivated by. I always like to show this image just because it makes me happy. This is a picture of my daughter, Aiko, who is 2 years old now. You can see here, she's a happy baby. She's smiling. She's doing what babies do best. She's slobbering all over the place, right? And mucus slobber is a polymer network, right, whose mesh-like structure helps to serve a biological function as being a biological barrier. And so by studying the dynamics of fluids and solutes and cells through these macromolecular networks, we also try to shed light on problems related to health. And so I won't talk about that today, but if you're interested, please feel free to check out our lab website. And so, as Sanjay mentioned that, these are really complex settings, complex media. Typically, they're very challenging to actually visualize things inside. Most porous media are opaque. And what we try to do in my lab is actually visualize those processes and somehow make these black boxes transparent. And that's what I'll tell you about today. And so our general philosophy is, I think, encapsulated very nicely in this quote by the famous New York Yankees ball player, Yogi Berra, who said, you can observe a lot just by watching. And that's what we try to do. By actually watching dynamical processes in these complex environments, we try to develop a better understanding of the fundamental processes and mechanisms underlying these dynamics. And so today I'll give you some examples. So first, I'll tell you about some of the work we've been doing studying how hydrogels absorb water and swell up in granular media, right? And this is motivated by the promise of hydrogels to serve as water reservoirs in dry soil for agriculture, right? This is an important problem. I'm sure you're all very familiar with the importance of being able to manage water more effectively in agriculture as conditions get more and more hot and dry, and water becomes more and more scarce. And so this is work that we published recently in a paper in Science Advances just a few weeks ago, and another follow-up paper in Soft Matter. These are available on our lab website. So if you're interested in finding out more, please take a look at our lab website. And so first I want to highlight the fabulous people who made this work possible. This project was led by a very talented postdoc in my lab, Jean-Francois Louf, who is now going to transition to being Professor Louf in a few months. He's moving to Auburn and starting a faculty position there. He worked closely with Nancy Liu, who was actually my first PhD student, who just became Dr. Liu, who helped set up some of these experiments. And actually, this project was initially started by a very talented undergrad, Maggie O'Connell, who developed the first prototype of what I'm going to show you. She's a graduate student at Northwestern now, and she was helped in that initial process by another former postdoc, Jeremy Cho, who's a professor at University of Nevada, Las Vegas. And I'm just going to show this picture again because I love it so much. I told you about my daughter who's 2 years old, and because she's 2 years old, any parents would know she goes through a lot of diapers, right? Babies go through a lot of diapers. Why? What are diapers useful for? They're useful for holding onto a lot of water. In fact, diapers are nothing more than packages that contain lots of hydrogels in them, right? What are hydrogels? Hydrogels are cross-link networks of hydrophilic polymers. So these are polymers that really love water. And so if you take one of these dry hydrogel particles, put it in water, what it does is the polymers want to stretch out and really expand and come into contact with as much water as they can, right? So this hydrogel swells up, it absorbs water, right? And so this is a measurement, for example, of the size of a hydrogel over time, and it absorbs water. Eventually, the polymers get so stretched out that the elasticity of this particle limits its further swelling, and so then it plateaus. Right. And so this is how hydrogel particles swell up and absorb tremendous amounts of water. They can absorb many, many, many times their individual dry mass in water and hold on to it. This is why hydrogels are useful in diapers, in trapping water. This is why they're also very promising as water reservoirs in agriculture. I just wanted to mention that these are squishy. This is a movie of an actual swollen hydrogel particle. You can see it's bouncy, it's squishy. These are squishy materials. And so hydrogels were initially developed partly for their promise in agriculture. The idea is that if you mix in hydrogels into soil, then when you irrigate your crops or when it rains outside, they hold on to that water. The water doesn't just bypass the plant roots, but the hydrogels hold on to that water. They swell up and absorb that water. And then over time, they release the water to the plant roots, right? And that reduces the burden for irrigation. And when this works, it works very nicely. So there are TED Talks on this where people claim, it improves crop yield with the same or less water usage, right? And there's this TED Talk that you can look up, Hydrogels as an Agricultural Solution. In fact, this TED Talk is what initially got me interested in this problem. And when you start digging, indeed, when these work, they work really nicely, but the results can be spotty. So, people mentioned that in other studies, sometimes the hydrogels don't absorb any water and they don't actually, serve as effective water reservoirs in soil. In some cases, they can actually increase the erodibility of the soil, which you don't want to have happen. And so there are spotty results. And the question is why? Why do, in some cases, in some soils, hydrogels work really well? In other cases, they don't work so well in holding on to water as for plant roots, right? And that's a puzzle that we got very interested in. And we decided, well, we're going to try to directly visualize this process within a 3D model soil to try to understand the conditions under which hydrogels absorb lots of water or don't. And how to tune hydrogels for different kinds of soils. And so the way we do these experiments is really simple. We constructed a box, essentially, with a transparent box. This is an early prototype where we just fill it with glass beads. This is our model soil, glass beads of a given size, right? We put the hydrogel inside of that packing. We fill it up to a certain depth. We fill it up with an aqueous formulation. And to mimic the fact that you put different hydrogels at different depths, and at different depths, you experience different amounts of overburden, right? There's more weight above you that presses on you. We can also apply a load on this packing. So it's a very simple idea. Here's a picture of Jeremy pushing on this to serve as the load. That's not a very effective use of his time, so we replaced him with weights instead that we can program to impose a given amount of load on this matrix. Right? And so here's an example of that. This is that very simple packing of glass beads, right? This is our artificial soil with a hydrogel embedded within it. You can see this orange thing. So you can see the hydrogel, right? No, not really. I mean, we see the glass beads, but we can't really see the hydrogel because the beads are just scattering light, right? And this is where we use a trick that we've refined over the years and we've applied in many cases. What we did is we formulated an aqueous-based solvent that the hydrogel still likes and it swells up in, but which has the same refractive index as the glass beads making up this packing, right? And so what happens when you infiltrate this packing with this solvent is everything becomes transparent, right? You no longer have light scattering off of the surface of the beads. And here's an example. Now we can see the hydrogel, right? It's right there, embedded within this 3D granular packing, right? And so this very simple idea is what we use to be able to actually directly visualize how these hydrogels swell in different model soils of different grain sizes and under different amounts of load. And so, just to summarize a lot of work, what we found at the end of the day is that if you just have a little bit of load imposed on this solid matrix, well, the hydrogel just swells up freely, right? It just swells up, it rearranges the beads around it, and it swells up to the same amount that it swells in just bulk liquid, right? In this case, it swells up to a sphere, kind of like a balloon inflating, absorbing all that solvent, and it swells to be 6 times its initial volume. And what we found, though, is that as you add more and more load, right, at sufficient load, what we found instead is that the core of the hydrogel didn't actually swell, didn't absorb any water. It only swelled up a little bit by fingering into the pores surrounding it, right? So in this case, hydrogel swelling is significantly hindered, and in this case, the hydrogel only swells to absorb something like 2 times its initial volume, right? And we can quantify this just by watching this process inside the porous medium, right? At low loads, right, the hydrogels remain circular, right? Whereas at high loads, they form these really weird fingery patterns, right? Shown here, the circularity goes down. And at low loads, they absorb more and their area increases over time. Whereas as you increase the load, they just hold on to less and less water, right? And so this seems to be part of the reason why these hydrogels aren't holding a lot of water in many cases. And so how do we understand this? So, this intuitively makes sense. You put a hydrogel under a lot of load, it's going to swell less and absorb less water. How do we quantify this? How do we kind of develop some general principles that quantify this observation? So first, let's talk about a hydrogel swelling just in bulk liquid without any confinement. In that case, right, the hydrogel initially starts as this dry sphere here, shown by the darkest circle, right? And as it comes into contact with water, as it absorbs water, right, it swells up. The polymer volume fraction goes down. So that's phi here, right? That's the amount of polymer occupying a given volume, right? So the polymer volume fraction goes down. And actually you can calculate using very simple thermodynamics what the swelling pressure, what the osmotic pressure associated with that mixture of polymer and solvent is, right? So the polymer wants to stretch out and swell up and really kind of contact as much solvent as possible. It wants to mix with the solvent, right? So when the hydrogel is first dry, that's shown here, it really wants to swell up and absorb lots of water and mix with the water, right? That mixing osmotic pressure is high. But as it swells up, the polymer volume fraction goes down. It has more and more water in contact with it. And that driver for mixing goes down, right? And this is something that you can quantify using what's known as Flory-Huggins thermodynamics. That's what I'm showing you here. And that mixing, that drive to mix and swell up is balanced by the elasticity of this hydrogel. I told you that as this thing swells up, the polymers pull back and they resist the expansion of this hydrogel. That's given by also, that's a classic expression in polymer network and elasticity. This is given by the Flory-Rayner expression. All these parameters depend on the properties of the individual polymers, but the punchline here, right, is that the desire to mix, right, goes down as this hydrogel swells, and it's resisted by the elasticity. And when these two pressures balance, that's the equilibrium degree of swelling, right? That's when the net swelling pressure goes to zero, and that determines what the equilibrium fully hydrated size of the hydrogel is. Okay, that's given here by RW, the wet, fully hydrated hydrogel size. That's just for a hydrogel in bulk liquid. What about a hydrogel in soil? How does this picture change? In a soil or a granular medium, right now, this hydrogel, as it swells, it has to push on the beads around it, and the beads around it push back on it, right? So this is a bead in contact with a hydrogel. There's a contact region of size A, right? And so there are several different competing forces here. There's the load on this matrix, right, which is transmitted through these beads, right, as the beads contact each other. And the force transmitted by these beads is given by the stress on this matrix times the area of a bead, right? So that's the force transmitted by a bead on the hydrogel. That's the force that the beads push on the hydrogel with. As the hydrogel swells, it pushes back on the beads, and that force, right, is given by the osmotic swelling force times the area of this contact region, right, at which the hydrogel is pushing on the beads. And that's actually something that we can estimate using typical Hertzian contact mechanics, right? So this depends on the amount of load on this matrix, the size of the hydrogel, the size of the beads, and the elastic modulus of the hydrogel, which we measure at different degrees of swelling. Long story short, as the hydrogel swells, it's pushing on the matrix surrounding it. The matrix pushes back on it, right? And at equilibrium, these forces must balance, right? And that determines how much the hydrogel swells by in this granular packing, right? And so as the hydrogel swells, right, this force goes down, this force is constant, and now you reach a new equilibrium, right, where the swelling of the hydrogel is hindered because of the forces exerted by the surrounding matrix. And we can solve for this. You can solve for this new equilibrium. As you increase the load on this matrix, you're squeezing on the hydrogel more, right? And this equilibrium goes down. So this very simple force balance, right? Balancing the swelling force exerted by the hydrogel and the confining force exerted by the surrounding matrix, right? Can help us predict how much the hydrogel swells by, how much water the hydrogel absorbs at equilibrium. And so we can test this. So we performed experiments where we were watching the hydrogel swelling or not swelling in confinement in these granular packings, testing different bead sizes, testing different hydrogel properties, testing different loads. And what I'm showing you here on the y-axis is that osmotic swelling force. So this is determined by the properties of the hydrogel. This is how much it swells by and pushes on its surroundings. On the x-axis here is the transmitted load, which depends on the properties of the granular packing and the amount of load applied. And for all of our experiments, testing different bead sizes, different hydrogel properties, different loads, we find really nice agreement over 4 decades, 4 orders of magnitude between these two forces, right? This very simple force balance determines how much water the hydrogel absorbs. Right? It determines this final equilibrium point. And, these are model experiments in these artificial soils. We said, what about real hydrogels and real soils? So we actually dug in the literature and we found published measurements of hydrogel swelling in different soils of different grain sizes and under different depths. We took those data, put them within our simple force balance, and we found excellent agreement. Again, this simple force balance can capture how much these hydrogels absorb water in different kinds of actual soils with different grain sizes and under different loads and different depths. So this is, just what we've done. A lot of other work in this area, but this is just one small vignette where I wanted to show you how just by watching this process, we were able to find that when these hydrogels are confined, they deform more and they swell less, as you might intuitively expect. But by actually visualizing this process, we've been able to go beyond this simple intuition, quantify it, and show that this extended version of typical hydrogel swelling theory that we've now modified for granular confinement, this very simple force balance determines how much the water the hydrogel holds on to, right? And I didn't show it here, but it also determines how much the surrounding matrix deforms and rearranges. And so now that we have this kind of more general quantitative understanding, now we can say for a given soil of given grain sizes and at a given depth, this is the kind of hydrogel that you need. This is the kind of hydrogel cross-linking and stiffness that you need to optimize, to maximize the amount of water that you're going to hold on to. So we hope that these insights can actually help improve this process in real agricultural applications. So that's one example of how just by watching dynamics inside 3D porous media, we can actually come up with a new understanding that hopefully helps improve these important agricultural environmental processes. So I'll give you another example of this, where we've been studying how colloidal particles distribute through 3D porous media. And so this is something that we also published last year in Science Advances. We have some follow-up work in physical review fluids and some other related work where we've synthesized different nanomaterials that we published last year in ACS Central Science. And I want to highlight the people who made this project possible. This project was led by a very talented postdoc, Navid Bismarck, who worked very closely with Joanna Schneider, an extremely talented graduate student. And they're co-advised with my colleague, Rod Priestley. Rod's lab specializes in the synthesis of different kinds of functional nanomaterials, and that's something that we're continuing to explore now. But, our motivation for studying this process, we have multiple motivations for studying this process. One classic motivation is just understanding basic filtration processes. This is a classic problem, right? You have dirty water with all sorts of particulates and junk in it, and you want to get rid of those particulates. How do you do it? One way to do it is to just pump that water through that feed raw water through a granular filter, through a deep bed filter. The idea is that some of those particulates get stuck in some of the pores, they get attached to the solid matrix, and what comes out is clean water, hopefully, right? And you want to be able to optimize the throughput of that. You want to decrease clogging, but maximize how much of the junk you actually trap, right? And so this is typically a black box where you can measure what goes in and what comes out and try to infer what's going on inside, but we wanted to do better and actually visualize that. And so that's what I'll tell you about now. Another big motivator for this project is something that Sanjay is an expert on, right? And that we only, are learning, still learning about. It's in trying to understand how things like microplastics and other naturally occurring colloidal particles distribute through the environment, how they can potentially pick up contaminants along the way, right? And so this is an important problem to be able to tackle. Just a simple question of how do certain colloidal particles of a given surface chemistry and size spread through an environmental porous medium, through soils, through sediments, through groundwater aquifers. How does that depend on the ambient flow conditions? How does that depend on the properties of the porous medium? Those simple questions are very challenging to answer, right? Partly because we can't actually watch this process. And so typically what people do is either they focus on individual grains, right? Where you have many different processes by which colloidal particles can get stuck or unstuck and transported, right? Focusing on an individual grain or a collector as it's sometimes known, right? There are many different processes. For many of the applications that we're interested in, the Reynolds numbers are all less than 1. So inertia typically doesn't play a role. Gravity also doesn't play an appreciable role at these length scales and time scales. And the Peclet number is typically much greater than 1. So diffusion also often doesn't play a role in what I will tell you about today. And so, we have these kind of simple studies that you can do where you just focus on one grain or one obstacle. And people have shown how, by changing flow conditions, these particles can get deposited on this grain in different ways, right? People have started to show how in periodic arrays of sparsely distributed obstacles, how these deposits can grow and merge and do all sorts of weird things. And people have also started to explore the influence of changing chemical conditions. So for example, if you change ionic strength, how does that change this process by which colloidal particles get stuck or not in these porous media? This is at the scale of individual grains, right? So that's one end of the spectrum. The other end, which is the more complex end, of course, is you can take real full 3D complex porous media, right, and just inject suspension of colloidal particles into it and measure what comes out, right? These are breakthrough curves or tracer tests, where here, for example, just by looking at the concentration of particles in the effluent, right, over time, you can see eventually some particles break through, right? And by taking curves like this, people try to infer what goes on inside the porous medium, right? But there's a lot that goes on. It's a complex problem. And so, while these give really valuable insights, they often don't fully shed light on what's going on inside these porous media. And so our goal in this work was to bridge this gap between studies of just single grains and studies of macroscopic porous media, where you just look at what comes out and look at what comes in. And so the way we do this, again, is by using the same trick, index matching. So what we do is we make our own model 3D porous media by taking glass beads. So they're slightly polydispersed, but they have the same mean size, right? Packing them together inside a quartz capillary. So these are typically millimeters or centimeters across, right? The beads are typically tens of microns, hundreds of microns in diameter. And then what we do is we fuse them together by sintering these media at 1,000 degrees Celsius for a few seconds. So the glass softens, the beads fuse together, and then you get a nice rigid porous medium that's non-deformable. And, so that's something where we can control the structure of these media very nicely, but they're still opaque, right? This is a top-down view of one of these packings. You can still see it's opaque because light's scattering off the bead surfaces. But what we do again is we formulate fluids that have tunable densities, viscosities, interfacial tensions, but have the exact same refractive index as the glass. And so when you infiltrate the pore space, everything becomes transparent. I promise you that packing is still there, but now you can see through it because now it's infiltrated with one of these refractive index matched fluids, right? By selectively dyeing the different components, by selectively labeling, for example, the colloidal particles and the solvent, we can interrogate everything in 3D using confocal microscopy, right? So for example, here, I'm just showing you slices that we've taken throughout one of these porous media at different depths, where we've just made the solvent filling the entire pore space fluorescent. So that's the bright regions. And these dark circles are cuts through the spherical beads making up the solid matrix, right? And by taking many of these slices, you can then put them together and reconstruct the 3D pore structure, right? So this is just one small view. We can do this for the entire porous medium. And so this is a trick, again, that we've refined over the years. We've done a lot of work using this very simple trick. We've been studying how polymer solutions flow through porous media. We have a paper that we put on the archive recently reporting some of this. I'll tell you about our work on colloids right now. We've also been studying immiscible fluids. So what happens when you have non-wetting fluids that infiltrate the pore space, right? Like non-aqueous contaminants, like chlorinated solvents. So this is something that we've done a lot of work on over the years, and some of the papers are listed here. Feel free to check out our lab website if you're interested in them. But to study colloidal transport, we do, again, the simplest possible experiment. We just take a dilute suspension of colloidal microparticles, right? And we just inject them through this, into this porous medium, right, at a fixed pressure drop. And the flow speeds that result are typically something on the order of a few meters per day, which mimics, like a force gradient flow in groundwater, a groundwater flow in sand aquifers. And to study colloidal deposition and to study the influence of surface chemistry, we used polystyrene microparticles, 1 micron in size. So polystyrene is actually one of the most prevalent microplastics. So these are microplastic particles where we change the surface chemistry. One set is amine modified. So these are positively charged. So they're electrostatically attracted to the negatively charged glass beads making up this porous medium. And then another class of particles is exactly the same, but now they're carboxyl modified, they're negatively charged, they're electrostatically repulsive, right? So this is a sticky interaction, this is a non-sticky interaction. And the question is, how do these things distribute through the porous medium, right? This is the simplest possible question that you can ask. So first, let's look at the sticky case, right? Our guess was, well, the particles, like the solid matrix, as we inject them, they should just aggregate on the solid surfaces, clog up the inlet, right? And they're just going to be localized to near the inlet of the medium. That's not what we saw. So here is a cut through this porous medium at a given depth within it, right? So here the black circles are the glass beads making up the solid matrix. The bright region is the solvent infiltrating the pore space. And what you're going to see is red stuff coming from the left. That's the colloidal particles that are being injected from the left. This is at a pressure drop, a pretty high pressure drop. This is a pressure drop of 260 kilopascals. So several atmospheres. And this corresponds to flow speeds that again are several meters per day. And here's what we see. And so again, I thought that the particles are just going to localize near the inlet because they're sticky to the solid matrix. That's not what we saw. I'll play this movie again. What we saw is that these things somehow managed to deposit throughout the entire porous medium, right? Which was a real surprise for us. You'll also notice, I'll play this movie again, there's some flickers that go on. If you look, for example, over here, you'll see some regions disappear and then reappear downstream, right? There are some interesting dynamics that are going on here that somehow underlie this deposition throughout the medium. So what's going on? Right? So as these things deposit, by the way, we can use this imaging to quantify the fraction of the pore space that's filled with particles, right? It increases as deposition progresses, as we inject more and more of the suspension. And because we also measure the flow rate across through the medium, right? We can determine the permeability, and the permeability goes down as you get more and more particles filling the pore space, right? So what's going on? So we can zoom in and look at the actual colloidal dynamics. And here are two examples. And what we see is that these particles, they deposit on the upstream faces of these beads, as we expect. They form these large aggregates. But what we see in many cases, and I'll play these movies again, if you look at this right movie, you'll see these deposits form, and then they disappear. They get eroded, they get pushed through the pore space downstream, and then they reform, they regrow, and they get pushed down again, right? So we find that there's this dynamic steady state where the particles indeed do deposit on the solid matrix. These deposits grow, but also they become eroded and pushed downstream. And that's why we get this observation that these particles distribute throughout the entire medium, right? There's this continual erosion and redeposition. And we can understand that quantitatively. So actually, because we measure the flow rate, we know the permeability, we can actually image the deposition, we can just do a very simple stress balance. We can compute the pressure drop, the viscous pressure drop associated with that flowing fluid across one of these deposits. And under these conditions, that pressure drop is larger than the yield stress of these colloidal deposits. That's the amount of stress that you need to put on one of these deposits to fluidize it and cause it to deform and continue to squeeze through the pore space. Like toothpaste. With toothpaste, it's a solid, but then you squeeze the tube hard enough, and then the toothpaste fluidizes and comes out, right? Here, the flowing fluid fluidizes these deposits and forces them to get pushed downstream, right? And indeed, if this picture is correct, then if we reduce the pressure drop across these deposits so that it's lower than this threshold, then we shouldn't see this extended deposition throughout the porous medium. And indeed, that's the case. When we reduce the pressure drop, right, we see that the deposition is localized to just near the inlet. And in fact, you know, again, this medium clogs much more rapidly, and the permeability goes down much more rapidly, even though here the pressure drops are lower, right? And it's because the fluid cannot squeeze the particles through the pore space, right? And indeed, under these conditions, the pressure drop across these deposits is lower than this threshold yield stress that you need to overcome to push the particles through the pore space, right? So that was for the sticky amine modified case. When the particles are repulsive, what we found is very similar behavior actually. At high pressures, the particles get pushed throughout the entire medium. Again, as we inject more and more of the pore space gets filled, the permeability goes down. But when we zoom in, what we see is, in this case, the chemistry of the particles changes where they deposit. Now they're not depositing at the upstream faces, but they're depositing at these tight pore constrictions where they're getting strained. But still, the flow of the solvent around these deposits can cause them to deform and rearrange and get pushed through the medium and redeposited downstream. And that's why they can migrate throughout this entire porous medium. We again find this dynamic steady state where again, the pressure drop across a deposit exceeds the yield stress that you need to push it through. Whereas when you make the pressure drop lower, right, we again have deposition localized near the inlet, right? The medium clogs more rapidly, the permeability goes down more rapidly, and in this case, the pressure drop across these aggregates, these deposits, is insufficient to cause them to yield. So we've done a lot more work using this platform, looking at how these particles interact with immiscible fluids, looking at how this influences the permeability of the medium. But in the interest of time, I'm just going to leave it here and again highlight that just by watching this process of colloidal deposition inside these 3D porous media, we've been able to show how these simple interactions between the colloids, the grains, and the flowing fluid can impact how these particles deposit through the porous medium in really interesting and surprising ways, right? And by taking these kinds of movies, our goal is to be able to develop a deeper understanding of the fundamental processes that control how colloidal particles spread, and thereby can predict and control spreading in environmental conditions. That's our ultimate goal. And so I think I probably just have a few more minutes left. Is that right, Sanjay? So I'll wrap up very quickly just by saying, just by highlighting another example of the work we've been doing in this area, looking at how microbes spread through porous media. I won't go as deeply into this, just in the interest of time, but this is something that we've been developing over the years. Some of the key papers are listed here. And our goal, again, is simply to understand how microbes spread through 3D porous media, right? Most of and when I say microbes, I'm specifically referring to bacteria. And, we've been studying bacteria for over 300 years as a community, but most studies focus on bacteria in liquid culture test tubes or on flat plates. But most bacteria live in your body, they live in soils, they live in sediments, they inhabit crowded, tight, porous media. And our question was, how does inhabiting a porous medium change how microbes spread? And so I'll just highlight the experimental platform we came up with to study that question, to address that question. Again, we make our own 3D packings of particles. These are our 3D porous media, where now the particles are not glass beads, because the typical formulations that we use for index matching make the bacteria very unhappy. In many cases, they kill the bacteria, right? Here, we need to keep them alive, we need to keep them happy. So what we do is we actually make 3D porous media using hydrogels. We pack biocompatible hydrogels together, right? And we swell them in cell culture liquid media containing all the nutrients and salts that the bacteria need to survive and to thrive, right? These are completely transparent. By tuning how densely packed the particles are and the particle sizes, we can tune the pore size distributions very precisely. And I'll just give you a highlight of some of the imaging we can do. So here's a movie of E. coli. So the cell body is shown in green. The flagella that help push it along are shown in magenta. This movie will loop, moving in these porous media, right? And one of the big surprises that we found was that, with E. coli, the typical way they move is what's known as run and tumble motion, right? This is how we understand how E. coli move. Turns out that they don't exhibit run and tumble motility in porous media. They move in a completely different way. And so that's part of what we've discovered just by watching. We've also been able to show that concentrated populations of many cells can collectively migrate over large length and time scales in porous media. And so we've been deciphering this process, again, just by watching it. And so we have a paper coming out in Biophysical Journal soon that reports some of this work. And so with that, I'm just going to conclude here. I think my time is up. Just by saying, again, going back to this original quote by Yogi Berra, you can observe a lot by watching. I hope I've shown you through these examples of how by doing in situ imaging, so by actually watching gels, colloids, bacteria in 3D porous media, where we can control the properties of the medium and we can visualize those dynamics, right? We can bridge black box models of the full-fledged natural system at the macro scale, right? And idealized studies in uniform environments or at the scale of individual grains. And that way we're hoping that the fundamental insights that we generate can help inform improved models of transport and spreading in natural environments. So with that, I'm going to conclude here. This is my amazing lab who actually make this work happen. Our lab website is listed here. If you're interested in anything that I just talked about, feel free to check out our papers. We're on Twitter. My students made me join Twitter, so we're on there as well. Thank you all for listening. I'd love to hear your questions.
Thank you so much. This is after a long time I am watching movies. That's how.
Right. We're not as good as Hollywood, but you know.
I think there are some questions on the chat windows. I'm going to read.
Let's see. Do you want me to? I have.
Go ahead.
Yeah. Okay. Thank you. So let's see. So someone asked, would the swelling for each polymer sphere of the hydrogel swell similarly for a different specific load? Since the pressure is applied evenly, or does the distribution of load across the hydrogel cause variation? Oh, I think you're explaining it right now. Thank you. Okay, good. Well, that's a great question because the whole point is it's not uniform across the hydrogel, right? The being in a granular medium, right? The forces are heterogeneous. The distribution of forces are heterogeneous. It's spatially non-uniform along the surface of the hydrogel, and that's the key. Is we had to update the typical theoretical framework that people use to model hydrogel swelling, which just assumes no stresses or uniform stresses for the case where you actually have these discrete contacts, right, that are inherent in a granular medium, and that actually plays a big role in determining how much it swells by. I hope that answered your question.
Yes, thank you so much.
Thanks for the great question. Someone else asked, very interesting talk. Thank you. Thank you. My question about part 2 is, could the repulsive forces amongst the amine modified particles, so those are the sticky ones, themselves also be playing a role in the way they're distributed in the medium? Great point. A competition between amine repulsion versus amine medium attraction. That is an excellent point, right? And all of those colloidal, and the short answer is yes. All of those colloidal interactions, okay, so again, you know, we've done, by the way, in that paper, if you take a look at the SI of that paper, we actually have really extensive hydrodynamic simulations of these colloids interacting with the grains and interacting with each other, where we put in the full DLVO calculation of the colloidal interactions along with flow and solved the full-fledged problem, and we found good agreement with the experiments. But you know, it's that we weren't satisfied with that because it's very hard to generalize that, right? I don't want to tell people, oh, you have to solve for every single interaction in every single problem that you do. Those interactions are important and they're subsumed into this yield stress that I mentioned. So if you have stronger repulsive interactions between the colloids, right? If they're more, you get fluffier aggregates that yield more easily, right? If they're more compact and cohesive, then the yield stress will be larger. And so those are important interactions. And we think that you can more generally incorporate them by thinking about the yield stress, which is that material parameter that determines how effectively you can squeeze these deposits through the pore space or not. I hope that answered your question.
Yes, absolutely. Thank you very much.
Thank you. Great question.
Oh, I had a question about the flow rates that you were using. Did you know what range it was for the experiments that you were conducting?
So I assume you're talking about the colloidal particle spreading?
Mm-hmm. Yes.
Yeah. So again, I apologize for the weird units, or maybe it's not weird units, but Typically our experiments, so we fix the pressure drop, not the flow rate, but the the flow speeds, I'll tell you the interstitial flow speed, right, which is the flow rate per unit area. The typical flow speeds, or the Darcy speeds, are typically on the order of, they range between 0.1 to 10 approximately meters per day. So that's why I apologize for the weird units. I don't know what your preferred units are, but that's a typical range of interstitial speeds that we explore. But we've broadened that since. That was just in that one study. I hope that addresses your question.
Yeah, thank you.
Anyone else? Yes, Sujit, I admit my understanding of hydrogels didn't extend much beyond boba, honestly. So, this was fascinating. I was curious. So my interest is on the microbiology side, and then we do subsurface transport of microbes for pollution remediation and all kinds of other applications. Right. So these are E. coli. When they're still moving, looks like it's a low cell density. When cells start to produce enormous amounts of biofilms, then the mechanics, I understand a little more about the microbiology and the chemistry of the biofilms, but in terms of the relative clogging of pores and just the mechanics, do you have comments on that? And again, implications in, like you said, environmental and agricultural fields where they would be applied.
Yeah, that's a great question. And I kind of skimmed over the microbial stuff, even though that's one of the most active areas, I think, actively growing areas for us, just in the interest of time. But that is a great question. So actually, part of our motivation, actually the biggest motivation for those studies was bioremediation, and also in agriculture, just understanding how rhizosphere bacteria move through soil, migrate to plant roots, form biofilms, and colonize plant roots. That's one of the biggest motivations for us. So, we started out studying E. coli because it's a nice model organism. It's, well characterized, but we've been extending that work since. So we've started working with Pseudomonas putida, which is, as I understand it, is very relevant to environmental problems. We've also been working with Pseudomonas aeruginosa, and the strain that we've been working the most with is Vibrio cholera, which forms biofilms. And we have mutants that form EPS, EPS polyside matrices, where we can knock out different components. And so what we've been doing there, so you mentioned clogging, which is very interesting. So what we have found is with biofilm forming strains, okay, so there are a few things that we found that are really fascinating. One is that it seems like, depending on the pore size, in some cases, if the pores are large enough, then the cells can just continue to swim through and, spread out and unimpeded. When the pores are sufficiently tight, then due to polymer secretion, they can clog the pores, become localized, and just form surface attached biofilms. So that's actually a transition mediated by confinement that we found and that we're kind of characterizing in detail right now. So that's one example where biofilm formation is really important. But there are several other things that we've been doing that I'd be happy to tell you more about, some other time. But most of the work we started with was just focusing on planktonic bacteria, E. coli, where we just wanted to answer the question, how does being confined in a crowded, tortuous pore space change how they move, change how they chemotax, and sense chemical stimuli? And it turns out to have profound consequences on just basic motility. And so that was our starting point, and we've come up with kind of improved predictions for predicting how they spread out over large lengths and time scales. And now we're trying to move beyond that to look at how growth is affected, how biofilm formation is affected in different other strains. And so that's our newest work.
That is really fascinating. There's like 10 different things that I can already think of, working and asking, but several of my students are here on the call, and I'm sure they're scrambling to pull up your papers now. Shruti
Awesome.
says, because we're now thinking, oh, we could package nutrients and oxygen releasing compounds and other things in hydrogels. So Kshitija, do you want to ask your question?
And by the way, I'd be very happy to chat more, whenever you want. We're always on the, we've developed all these, I think, very interesting and useful experimental tools, and we're always looking for, useful and interesting scientific problems to tackle. So I'd love to talk more whenever you want.
Oh, we got problems. Yes, we are happy to.
Well, hopefully we can come up with solutions.
Yes. No, that was that way. Yes, of course. Yes. So Jerry and Kshitija and another student works on antimicrobial hydrogels for various applications. Yeah, go ahead, Kshitija.
Yeah, just speaking off of what Dr. Mahendra said about packaging things, has your group been able to do any kind of testing to see how things that were absorbed by the hydrogel can be released back into the environment?
Yeah, that's a great question. So, no. A short answer is no. I think it's super interesting. For everything we've done so far, the hydrogels are essentially just inert and an inert background. Mm-hmm. That being said, we have other work that I haven't talked about here, where we do a lot of also hydrogel synthesis and in different ways. We've been making hydrogels for atmospheric water harvesting. So we've been using thermoresponsive hydrogels with hygroscopic polymers in them to essentially absorb water from air, and then you heat them up a little bit and they release it in liquid form. So that's kind of something fun we've been doing. The reason why I mentioned that is because using these thermoresponsive polymers, so they're polymers where you just heat it up by a few degrees, let's say above 32 degrees Celsius, then it becomes hydrophobic. It goes from being hydrophilic to hydrophobic, and then it collapses. And there are these big shape changes that happen. This is very well studied, and that's something that we've been using to essentially cause hydrogels to collapse and release their contents in different ways. The way we've been doing it is, or the application we've been targeting is basically to just get water from air. But I can envision how we could use similar synthetic approaches to do what you're suggesting. We've never done it, but I think that's a great idea, and that's quite plausible. I hope that addresses your question.
It does, definitely. Thank you.
Maybe I'll just add one quick thing as a teaser, okay, in case this is interesting, maybe or maybe not. If we're out of time, then that's okay.
Some students are dropping off to go to class or something. Well, I could stay for a few minutes.
Well, I'll just say very briefly that something again that we've developed in the on the microbes side. We reported part of this in that paper that's coming out in Biophysical Journal soon. So we've actually figured out ways to 3D print inside these porous media, inside these hydrogel porous media. When I say 3D print, we can 3D print essentially polymers and polymer networks. We can 3D print various kinds of soft materials. We can 3D print microbial communities. We've actually figured out a way to 3D print, in principle, any microbial community of any complex 3D architecture and composition that you want. And so again, that's something where we're very excited about using this approach to engineer complex microbial communities. And maybe that's something else that some of you might be interested in.
Well, definitely different areas to approach that. But yeah, I think this is so cool. Now I'm going to scramble and look at your paper when it's published. So congratulations and thanks again for your time.
Thank you, everyone.
Yeah, so I am going to stop recording. Sanjay, did you have any final thoughts?
No, I think you can stop recording. Then I'll have something to say.